Okay, why don't we get started? Welcome everybody. Good morning. And my name is Jeffrey Slotnick. I'm a technical fellow from Boeing Commercial Airplanes, and I'll be the chair for the session this morning. Just wanted to give you kind of a description of related sessions. So we have two high-lift CRM sessions today. So one now and one in the afternoon. We'll have a panel session at the end of the second one in the afternoon, so please stick around for that. And then tomorrow morning there is a related topic session on CFD validation on a broader range of topics that's related to the ecosystem as well. So hopefully you'll be around for all three. So the way this works today, the two sessions today are about 100 minutes a piece, so everybody gets 25 minutes of presentation time. Typically, we'll be targeting about 20 minutes worth of a presentation and 5 minutes worth of questions. We may have to push off the questions until the panel, so just be aware that we'll try our best to stay on track there. So, so with that, let's go to the first presentation, which I'll be giving. Again, my name is Jeffrey Slotnick, for those who just walked in. I'm a technical fellow at Boeing Commercial Airplanes. I've been doing CFD aerodynamics for almost 38 years, a long time. And a lot of this has been focused on low-speed aerodynamics for a good chunk of my career. So we're going to talk about something that we started almost 10 years ago, actually. That's just now kind of gaining momentum and fruition. You'll see a lot of that. So I'm going to talk about the overview of the ecosystem, and then the following presentations will be individual partner activities associated with the ecosystem. So we'll have my presentation, there will be 3 others this morning, then there will be 3 others in the afternoon, then again followed by the panel. So let me just first say that although I am presenting this morning, the work that you'll see really spans multiple organizations over many, many years. Many of the people in this room are intimately involved with the ecosystem, have been playing a huge role. So I am representing a lot of different people. So, all right, next start. Oh, it's me. Sorry. Left button. Okay. All right, so as an overall sort of agenda here, I'll talk about some introduction, some motivation behind the work that you'll see. There is a CFD validation strategy that is critical really to doing the work that we want to do in the ecosystem. It kind of drives what, the direction that we're going in, and it guides what we do as we're learning. And so there will be a lot of, well, I'll get to some of that in terms of what we've learned so far. But so this validation strategy is really important. Again, it kind of keeps us on track of what we want to try to do. So I'll talk a lot about the ecosystem, what it is, where it came from, and its origins. And then the critical part of the ecosystem is actually wind tunnel testing of the high-lift CRM. And so there's wind tunnel testing campaigns that I'll touch on, a lot more details in the paper. We'll talk about some current status of what we've already learned. So we're kind of in the middle of a lot of the testing that we have planned in the ecosystem. There will be a lot more testing in the future, and then there will be spin-offs that we'll talk about. And then some closing remarks. Okay, so as we've heard over the last several days, there are some pretty ambitious goals really to address climate changes. And so net zero by carbon by 2050 is a huge goal, both here in Europe and the United States. And around that, in terms of aviation, is sustainable flight, lower emissions, of course, and then generally efficient air transport travel. And so to meet those goals, we're using computational methods more and more, as we have been over the last 20 years. And we need to make sure that those tools and the emerging tools that are coming online are accurate, efficient, and robust for particularly design and analysis of commercial airplanes. So the image you see here on the right is the standard operating envelope image that you've probably seen 1,000 times. So you have speed versus load. And so the things here in the middle are areas where we have used typically Reynolds average and Navier-Stokes CFD methods over the last 20 years and have really calibrated and validated those methods for use at the cruise point, essentially at 1G. Typically high speed, but also in certain areas low speed. What we're trying to do, particularly with low speed aerodynamics, is push the utility of these tools and these emerging technologies to the edges of the flight envelope where the physics becomes much more complicated. We'll get into that. And so that's what we're really trying to do. And the ecosystem, particularly that we're going to be talking about today, is really trying to push low-speed aerodynamics. Okay. So to do all that, you need, systematic, truly systematic CFD validation of these technologies. And so that's what the ecosystem is really all about. So as I mentioned, the focus here is on low-speed aerodynamics. Obviously, the edges of the flight envelope encompass a whole broad range of aerodynamics, but we're really focused on low speed. And you see the image on the right. This is an image that we kind of worked with Airbus in the past on to kind of explain why low-speed aerodynamics is so complicated, particularly high lift. You've got boundary layer flows, turbulent boundary layers that can have areas of laminar separate or laminar runs where you've got laminar to turbulent separation or transition. You've got vertical flows coming off of blunt bodies like chines, edges of flaps, and you've got all that interacting in nonlinear ways. So you have to be able to model all this in a CFD tool. So to drive where we want to try to do in using these tools, we have a validation strategy, and we'll talk about that in a second. And on top of that, we need really high quality test data to help validate these tools. And in the past, we've had some data on some configurations, but they've been very limited and of unknown quality, let's put it that way. And so this is an opportunity to really do CFD validation in a very systematic way with high quality data. And the focus of the ecosystem is really to focus on complete airplane configurations. We'll talk about the validation strategy around commercial airplanes, but there's also building block technologies and experiments that have been going on that kind of feed the full airplane configuration testing that we're talking about. Okay, let's talk a little bit about the strategy. So the way we look at this is we typically focus on things that are important to us, right? So, so you want to identify the aerodynamic characteristics of the airplane that are important to model. Okay, these can be typically lift, drag, and pitching moment at certain points in the lift curve, for example, or they can be very specific things that we want to target in terms of predictive capability. So stall is a very important aerodynamic quantity that we need to be able to predict. It drives landing field length, many other things. And what happens after stall is something that we design in the airplanes, right? We want the airplane to go nose down at post stall, and so that there's a lot of physics that's associated with that I guess maneuver, right? And so we want to make sure that we're getting the right answer for the right reasons, and we'll be saying this over and over again. The flow is so complicated that you have to make sure you're getting all the different pieces correct. So we want to characterize the governing flow physics. Typically, we're going to talk a lot about CO max, or the maximum lift at stall. That's really driven by separated flows. We know that RANS has basically issues with modeling separated flows, so there's a lot of focus on that, particularly in the early testing that we'll talk about. So we've done a lot of CFD work already over the last 2 decades, and we kind of understand where the gaps are in terms of our predictive capability, so we want to make sure that we focus on those gaps and shortcomings. And then we can then start thinking, okay, well, to get all that data, what configurations are of interest? So we define these what we're calling relevant test configurations. So the ecosystem has a baseline landing configuration, a baseline takeoff configuration, and many other parts of that. So we'll talk about that as well. So once you have those models built, you acquire the critical experimental data. And so there's a whole bunch of data that we really want to collect, and we'll talk about that. And we're getting more and more, high quality data that is different and perhaps beyond what we typically get. And then we perform the CFD validation. So we do that typically through community workshops, prediction workshops. So there's a high-level prediction workshop, for example, that we just completed. You'll hear a little bit more about that tomorrow. So that's the general way that we are kind of moving forward through the CFD validation activity. And the ecosystem, again, supports this. So let's talk about the ecosystem. So we recognized within Boeing over a decade ago that we needed to do some serious validation of our tools. And back then, it was really just RANs. We had probably 2, maybe 3 decades worth of experience with RANs. We had done a lot of work internally in assessing RANs for Boeing configurations. And we realized that, well, okay, we don't know it all. And so we want to engage the broader community. And so we started thinking about ways of doing that. And we wanted to take advantage of the learnings from the high-speed common resource model. So that activity had been going on for about probably a decade before that. And so we wanted to build on the high-speed CRM. And so in 2014-15 timeframe, we started this activity where we designed the lines for a high-lift variant of the high-speed, basically, CRM. And so we finished that in 2016. In the years after that, 2017, 18, 19, we socialized the availability of that geometry, essentially, and started bringing in relevant and interested partners into trying to do something really truly unique and systematic, and use that configuration for CFD validation. So we created this thing, what we're calling the ecosystem. And so we, over the ensuing 3 or 4 years, we pulled in a number of different organizations, and the idea was to build a CRM or a series of CRM configurations, models, wind tunnel models, test them in multiple places, and collect that data for CFD validation. The way this works in the ecosystem is partners basically fund their own activities. There's no written contracted funded activities of any kind. So partners come with their own money. They typically use that money to build wind tunnel models, we'll talk about that, or provide test data at testing facilities, or a combination of both. We agree to share data from the testing of those models to a certain minimum standards, minimum level. We can talk about that too. And then we provide that data, ultimately provide that data to the public. It's publicly available data. We get to choose in the ecosystem when that data becomes available, but eventually it does become available. And not all testing data is part of the ecosystem, so people can utilize those configurations, collect that data for whatever reason, and provide just the minimum set to the ecosystem. And so you'll see some of that as well. Okay. So let's talk about why this is important and why it's compelling for partners to get together to do this. So the high-lift CRM is truly a industry-relevant, publicly available data set. It's a unique, one-of-a-kind thing that is now available online at the NASA website. Anybody can download the CAD files associated with that. And it really forms a reference configuration. So that when we say reference, that means multiple groups of people can use the same exact geometric data, basically. And when used properly, you have a direct assessment between CFD and the experimental data that we're collecting within the ecosystem. That is a huge deal that people don't fully understand until you don't have that data and you really want it. The availability of the CRM high-lift geometry now allows people to build nearly identical models of the same configuration. Okay, that again has never happened. This is a unique opportunity to do that. And as we'll see, there's a lot of variations of testing that could then ensue when you've got multiple models that can be tested in multiple facilities. Okay. Again, this is a challenging geometry, but having it open source allows people to then collaborate, and that's really the key. As we collaborate, we learn from each other, and we accelerate learning overall. One of the key drivers of doing this, particularly, NASA has been a leader here and really kind of generated the first set of geometry and wind models for us, is looking at flow measurement technology. So as we go forward, the typical force, moment, and pressure, surface pressures, that's all good, but we need more. And as you'll see, we need more now. And so there's a lot of technologies that are being developed, typically flow measurement technologies, off-body, on-body, that will provide, again, an enriching amount of data for the overall ecosystem data sets. So that technology is being developed now. One of the things that's kind of overlooked is this pre-competitive nature of the configuration. So you could utilize this. So now anybody can use this to look at new aerodynamic technologies, different chines, different this, different, and do that in a collaborative way in a pre-competitive fashion. So it doesn't have to be tied to internal, industrial objectives. And then there's indirect benefits. So a lot of the partners are building these models to use as check standard models in their tunnels to train their workforce and so forth and so on. So there's a lot of, like I said, secondary benefits. Let's talk about testing objectives. So now we have this geometry, we have partners committed to building these models. What are we trying to do, and what are we trying to do in a consistent manner? That's kind of a key here. So we have the basic geometry. If you go online, we have CAD files that kind of describe all the different pieces of the geometry, but then we define specific combinations of those geometry into what we're calling reference configurations. So again, we have a reference landing configuration, we have a reference takeoff configuration, we have the ability to build up the model from a sort of a cruise wing body configuration all the way up to full landing with the landing gear and whatever. So that was all built into the ecosystem from the beginning. So the testing that is ongoing and that will be, in the future, we will be collecting data essentially for those configurations. Those are what we're calling the sort of the baseline configurations. The ecosystem data that we're hoping to collect will be around those reference configurations, in addition to other things. We want to utilize the testing in the most effective way to look at flow physics. So again, you can look at the forces and moments, and unless you understand what is actually happening in the flow, you may not understand, or you may get the right answer for the wrong reasons. And we've seen that a lot, particularly with RANs, as you get close to the stall. And so we want partners to not only collect ecosystem data, but really study the flow physics. And so surface visualization, off-body visualization, those things are like kind of critical. And we're learning that we wish we had a whole bunch of other data, right? Because there's the physics is so complicated that you need multiple corroborating sets of data to really understand what's happening. So that's really a focus. Now within, I would say, the industrial elements, we want to study Reynolds number. So clearly, Boeing is very interested in understanding what a high-lift system does at flight scale. So getting up to the highest Reynolds numbers possible is really a key objective. And so we have multiple partners now that can run at a range of Reynolds numbers. So we're getting data across a range of Reynolds numbers. We'll see a little bit more about that in a minute. Again, this enables the use of improved flow measurement technology. So, many entities, I would say, universities, for example, are developing technologies that are kind of giving us feedback and provide requirements in terms of model design so that we can actually incorporate some of those new technologies. What's really cool about the ecosystem is that once you start generating these wind tunnel models, you could, for example, test them in multiple locations, in multiple facilities. And that way you can study wind tunnel installation effects. Okay? And then, again, secondary objectives. So let's talk about the testing campaigns. So again, integrated testing, very collaborative. What I'm showing here is sort of the current state of the ecosystem testing. This is kind of just a graphic of what technologies are available and what models have been tested. So we have 4 models currently available. We're building or will be building another 4, so a total of 8. We're testing in multiple facilities. Certain groups of people that you hear about today are testing one entity's model in a different facility. So we've got multiple models in multiple facilities, and so we're trying to collect all that data. All that data, generally speaking, feeds the prediction workshops that are kind of shown here at the very bottom. So again, we'll have all but AERO talk about their individual contributions to the ecosystem. And this is just an example of what we have in the paper. So for each of the partners, we have really kind of laid out what it is they have been, what models are available, what testing that occurs with those models, and what the objectives are, really. And every partner has different objectives, right? And then what kind of data is available or will be available from that testing. So again, this is just an example of what we have in the paper for all the different partners. Our current status. So to date, we have, basically 4 different models, we have data at multiple Reynolds numbers, all the way from atmospheric up to 30 million in the NTF. And what we typically see, currently this is relatively new. So this is data that has been collected over, like, say, the last 12 months. So what we're seeing is expected trends in Reynolds number at both facilities, which is really good. Both the AERO F1 up to about 5 or 6 million, and then the NTF up to 30 million. However, what we trying to understand right now is the trend of some of the data in terms of family. So we would expect, if you're testing on the same configuration, that all this data would basically collapse on one another. And we're finding that that's not the case. And so we have spent a lot of time over the last 6 months trying to understand, why the NTF data, for example, is not familying with the rest of the data sets. And so there are ongoing activities to try to understand that. But again, it's the challenge of the ecosystem, right? This is something we did not expect. We are exploring, we're learning. The more testing that we do will illuminate what is happening here. And so the more data we can collect, particularly at, let's say, higher Reynolds numbers, the better off we're going to be. And we're in the process of doing that. So there are ongoing activities to try to understand what is happening here. All right, so I'm going to just close off with a few things here. So systematic CFD validation is really critically important to enable accurate prediction of low-speed aerodynamics. We have developed and have managed and are encouraging the use of ecosystem data within the ecosystem layout. Testing is ongoing, right? So we are continuing to collect this data, and we're providing that data through workshops. And so I want to kind of add or end with the opportunity. So one of the reasons why we're here this week is to really kind of explain and describe what we're doing with the ecosystem in hopes of generating a lot of interest. We're adding partners all the time to the ecosystem. People are coming out of the woodwork asking us, particularly for what we could do, for example, with either models or testing data or whatever. So we are very, very much open to working with anybody who's interested with us. So with that, do we have any time for questions? Yeah, one quick question. Any questions? Is it this one?
15.
This one?
This one. Yes, so it's actually quite interesting to see that the CL Max between the Honora FOGA F1 and the NASA NTF is actually quite different. Could you comment on that?
Well, that's really what this is, right? So it's just really these two data sets here. And so we have looked at everything. Let's put it this way. We have done an extensive amount of deep dive into what is going on. We're collecting, as it turns out, we're going to be collecting data in the 14 by 22 on the NASA model in next week, 2 weeks. So sorry to interrupt, what's the turbulence intensity difference? The free stream turbulence intensity difference between the two tunnels? So they're different.
Because
these are industrial tunnels, right? And
yeah.
So I'm not sure that we've done an extensive assessment of that effect, okay? But some of these models are full span, some are half span.
Okay.
So there's a number of different potential sources of error. Let's put it that way.
Okay, thank you very much.
Yeah, you're welcome. Okay, I think we should move on. Thank you. So our next speaker is Adam Clark. So Adam is a aerodynamics engineer at the Boeing Company. We work together in Seattle, Washington. Principal roles include implementing technologies to better predict flight characteristics for commercial airplanes. Adam has got a degree from Emory University and a Master of Science from the University of Washington.
Great, thanks, Jeff. So my paper is titled Challenges in Geometry Development for the CRM-HL Ecosystem. We'll talk a little bit more about what exactly that means and what we're trying to accomplish here. A couple of things on the overall summary here. We'll talk about the history, how we got to where we are today in defining the geometry, why there's another paper defining the geometry. We'll dive into some of the details of that, the specific reference configurations that we've gone out and actually defined within this paper. There's a number of details that were not captured previously that are showing to be experimentally important to have consistent between all the models in the ecosystem. Document some of those. We'll talk a little bit about deviations between the half a dozen models that exist already within the ecosystem, just to keep those in the forefront of people's memory. And then we'll talk about what it means to verify a model, both in the design phase and the production phase. And then also how do we keep all of the CFD geometry consistent with all the validation work we want to do here. Starting off with the history. So the original concept of the CRM has been around for almost 20 years, starting off with it was originally just called the Common Research Model. We've been referring to it now as the transonic CRM, just to differentiate a little bit. But it was initially, kind of trying to do the same things that we are in the high-lift ecosystem. It's a concept to build a model specifically for CFD validation. Again, a transonic configuration, pretty simple, just a wing and a body. So not a whole lot to complicate the geometry there. Seeing the success from that, we went on and said, hey, this would be really cool to have for a high lift variation as well. So back in 2016, maybe a little bit before that, we started working on it. But the initial definition was put out in 2016 at an AIAA conference. So basically what we did here is we took the transonic CRM, we modified the wing loft. There's a couple of things, additional constraints that had to go into the wing. For example, the leading edge radius was made a little bit more blunt, a little bit more amenable to high lift flows. We straightened the leading edge just to make the kinematics of deploying slats easier. And then we went on and defined the actual high lift surface lofts, so slats, slat extents, slat lofts, and flap extents and lofts as well. And that resulted in an initial definition of the high lift variant of the CRM. And then that paper launched a model, so there was a 10% model built based on that. Took that model to the wind tunnel and figured out how it performs, and then went forward and defined kind of the initial reference configuration. So we had an initial guess at where surfaces were oriented, that sort of thing, and then we went and tested it and said, hey, we need to tweak it, we need to optimize things a little bit. So this 2020 paper captured those initial reference configurations, just both for landing and takeoff. So since then, many more models have been built. We've learned a lot. We've figured out what it takes to be consistent between models. And the intention of this paper is really to capture some of those details, to document some of those formally, such that they're referenceable. So what we do here is we document and name some configurations beyond the initial reference landing and takeoff configuration. So the full landing configuration is what's shown in the geometry to the right. You have flaps deployed, you have slats deployed, you have a nacelle that's in place, we have a full empennage definition. And then we're also going to, as I mentioned, we're going to capture and document the details necessary to keep the models consistent between tests. We're going to, again, highlight the requirements to verify the models and share how we came up with the CFD geometry that's out there. So the reference configurations, starting there. As I mentioned, the initial reference takeoff and landing positions were previously defined. So that's the full reference configuration that includes all of the components. One of the key features of the geometry that is defined in the original paper is that it's modular, meaning there are pieces that can be added and removed to systematically expose aerodynamic features of interest. That's been widely adopted in all the testing that's been done so far, and had shown some pretty great value and success in the high lift prediction workshop that just happened in July. So this paper is formalizing and naming those configurations to ensure consistency across the variety of testing that happens. So we'll go through what those are, starting with the most simple. So this is the CRM-HL WB configuration, the wing body configuration. It is our simplest configuration. It's comparable to the original high-speed CRM, but it's, as I mentioned, it's using a different wing loft. So this is just simply the fuselage and the wing and the flap support fairings. From there, we can deploy a full span slat. So this is obviously no nacelle is in place here, but it exposes the wing slat brackets. It has a huge boost to our high lift performance. We get a very appreciable increase in stall angle of attack, but it does shield us from all the complex flow interactions that happens with the nacelle and with the flap. From here, we add the flap, the wing body slat flap, WBSF configuration. This is going to go ahead and increase your lift appreciably at a moderate angle of attack. Again, why we have flaps on airplanes. The reference landing position here is what's typically used for the flap position, but again, there's a full trailing edge position range that's available. And then the jumping to adding the nacelle takes us back to our full landing configuration, as we're calling the CRM-HL LDG for landing. So that's, again, adding the nacelle and the chine, removes the part of the slat that spans where the nacelle is. And this configuration can be exercised with or without the nacelle chine. A few of the further details that we found are important in our testing. So the first little bit is this gap that exists between the flaps. So the flaps themselves, we provide as full span lofts, not quite full span, but larger span than they typically would be. From there, they get trimmed, cut back from each other and from the side of body and from the end plane, such that they can achieve all of the deflection ranges that are defined. To provide that clearance, we end up with an appreciable gap between the inboard and outboard flap that has, again, an appreciable impact on the flow separation characteristics that you see on the flap, and as a result on the actual lift, so you can actually see this numerically. Typically on a production aircraft, we would seal these with flexible bulb seals. Obviously, it's much harder to do that at a 6% scale or smaller. So what we've done here, what's typical practice is to fill this gap with a moldable filler and tape typically. So that obviously can vary partner to partner just depending on how people do that. So we've provided consistent instructions on how to get that to be exactly the same amount across the ecosystem. Additional guidance, there's been a lot of stuff in the ecosystem that is provided kind of informally, just through emails. Hey, how do we do this? So the gap between the flaps is one of those where we have provided guidance to everybody, but this paper is actually formally documenting that. So we've taken the opportunity here to again formally document a lot of the stuff that's been passed back and forth informally. So that includes the pressure belt locations, trying to have as consistent of a set as possible of those between models. The slat bracket locations are explicitly defined here. We've gone forth and put out a set of trip dot curves, so the typical locations where we want the model tripped, and that includes for all possible configurations. Realized we never actually documented the reference quantities in either of the first two papers, so those are captured here. And then also the existence of a alternate trailing edge thickness set of geometry. So that's basically as you scale down to some of the smaller models. For example, we have a 2.7% model where if you took the same geometry that works for the 10% model, the trailing edge gets too thin to manufacture. So there's a separate set of geometry that's good down to the 2-ish% range. Deviations. So despite all of our best efforts, there have been deviations across the ecosystem geometry. They've been getting less and less with time, so this list is a little bit chronological. Most of what happened here is thought to be pretty minimal in aerodynamic impact, but it is important, there are geometries for, I think, every single one of these models out there that people are running CFD on, so it's important to realize that if you're trying to compare to a specific set of data, what is different between that? So starting with the NASA 10% model, that was the one, again, that was defined based on the 2016 paper. So things changed based on that first test. This one has a couple of loft differences. The nacelle contour was made a little bit more, or a little bit less aggressive. We saw some flow separation on the nacelle in that first test that we didn't want to be a feature of this model, so the nacelle was recontoured. The WUS, the wing under slat surface, so that's the piece of the wing that's exposed when the slat is deployed. Based on that definition happens based on the takeoff position, so you want it to seal wherever the slat ends up for takeoff positioning. So we ended up relofting that between the final reference configuration and what's on the NASA 10%. We did test both the preliminary and final reference positioning. This model features a spoiler trailing edge mismatch between the inboard and outboard. And then this one also had a adjustable chine position. And then another thing that's, consistent between a lot of models but not consistent with the reference configuration is the flap track fairings. We didn't have those defined in the ecosystem until pretty late, so the 10% defined their own, and that was carried on for a few subsequent models. Then the next model that was built was the Onera. They're calling it the LRM, the large reference model. That one has a few differences that are worth highlighting. They have a fuselage definition that was carries back to the transonic CRM days. They smoothed the nose of that a little bit. Very minor position differences in a couple of the surfaces, like the chine, the trim surface on the bottom of the pylon. The outboard wing under slat surface is preliminary geometry, just because of when that surface was available. But the slats are maintaining the correct reference positions. That drives some very small positioning differences to the inboard slat because we try to keep the critical distances comparable. The flap to flap and flap to fuselage sealing differences are a little bit different on this model, primarily because we didn't document that in time. And then again, the flap track fairings are based on the 10%. So then as we progress in time, we have the KHI and the NASA models. Both are using the legacy flap track fairing design. The KHI model is using the thicker geometry. And then you get to the most recent, which is still being built, the Boeing 6% model, and that's essentially an explicit copy of the reference configuration. Talk a little bit about model verification. So verification is kind of how do we ensure that what gets designed and what gets built matches the intent here. And there's really two different steps here. There's design verification. So we have a reference configuration. The geometry that we provide consists of lofts and positioning information. That's kind of left to the model designer to position things with that information and trim things. So there's room for errors to happen there. So this step is really to ensure that the as-designed model matches what we expect in the reference configuration. And then there's the build verification step, where we want to ensure that what gets built actually matches what was designed. So different levels of the verification have been demonstrated across the ecosystem. And I think as a result of that, there's quite a few uncertainties related to model conformity. Simply, people have checked things differently, and we don't know how close they match the design intents. So talking about design verification first, what we've done here is provided fully assembled reference CAD. So that's basically taking all of the geometric definition, trimming stuff, sealing stuff as it should be. That's provided kind of alongside the reference lofts. And what you can do there is take the as-designed parts and overlay them with the reference assembly. And it's a very easy approach to either visually inspect. There's a number of CAD tools that you could use to figure out where differences are. This is just a pictorial view of what it would look like to visually inspect in CATIA. So you can tell that differences pop out pretty apparently. So for example, on this model, all the kind of static-y area is two surfaces that are basically identical. And then you get into, this is just highlighting the nacelle recontouring that we did. But I think the green here is the original, and then the gray is the reference configuration. So you can clearly see where things change. And again, we're not prescribing a tool to use for this approach, but there's a number of different ways you can tackle that. Build verification is another step. So again, this approach, the idea here is to verify that the parts that you had manufactured, you provided drawings for, you provided CAD models for, get built per that drawing. So during manufacturing, it's most common to utilize coordinate measurement machinery, CMM checks. We've seen a variety of how this is done throughout the ecosystem. There are people that just CMM the individual parts. We've seen quite a few ecosystem participants CMM the full assembly, which is pretty dang helpful. If it's done correctly, it can be used to extract the positioning tolerances that we actually care about, but that gets pretty dang complicated pretty quickly. This is an example of a CMM on one of the NASA builds. So again, you can see a lot of areas where the discrepancy is zero. You can see some areas where things start to light up. One particular slat looks to have some positioning error here. So aside from this tells you a numerical value about how far out that is off from the reference surface, but it doesn't really give you what we actually care about, which is deflection, gap change, height change. So for leading edge and trailing edge devices, kind of in the order of sensitivity, we have a deflection angle, so how much the device is deflected. You have the gap between the device and the surface, and then you have the height on the slat and the overlap on the flap. So those three quantities really define the performance of the individual surface. That's really what we care about. So if we wanted to consistently compare model A to model B, I want to know these three quantities. That's not so apparent how to get that from a CMM. There have been people, Onera in particular, that was pretty clever about how they did their CMM inspection, was actually able to derive this data. But this paper is essentially highlighting that we really want to direct measure these. So we provide locations where the direct measurements should take place, methods to do so. So really highlighting that for everybody that builds a model, we want to have this data. And then last piece I have is on the geometry development. So equally important to the model build is, if we're using these models for CFD verification, or validation, sorry, we want to ensure that the CFD geometry explicitly matches what we're testing. So in addition to providing the reference geometry, we've kind of taken it into our own hands to provide a consistent set of CFD-ready geometry. So the models that basically the approach that we've done is we've taken all the parts that are ready to be built and simplified them in a consistent manner and provided consistent models across, most of the ecosystem models to date. And there will be more coming. So this is just an example of, kind of what the model itself looks like and then what it looks like running into CFD. So you can see that we, remove all the fastener holes that get taped over. The slat bracket itself is actually 2 different pieces. That's obviously, you don't want to try to build a grid on that. You want something solid. So just trying to do this all consistently. And I really think the only way to do that is to have one party take that into their own hands and just do that. So that's the approach that we're taking in the ecosystem. So in summary, we've done a lot to define and document the CRM-HL over the years. As the ecosystem expanded, we noticed some inconsistencies that kind of arose, gaps in our, what we documented. So this paper is really trying to close those gaps, ensure that the experimental data that we acquired on different models is ready to be compared. So we provided some details on how to verify your model and build. And then finally, we've provided an approach to build CFD-ready geometry. So that's what I had. Thank you.
So we have plenty of time for questions.
Are there any steps taken to ensure that the stiffness of the physical model is relatively consistent across the different builds, so you're getting similar aeroelastic effects for all the different ones being tested?
Yeah, that's a great question. Simply the scale and range of facilities we're testing in makes that kind of impossible, right? At the smallest end, we have a very stiff 2.7% model that gets tested in cryo environment. We have less strong 4% models that are built for 1 atmo. We have 10% models. All are architected very, very differently. So the approach that we've taken is just essentially saying, hey, we need to get that aeroelastic data and figure out how to correct for it in the CFD. So there's not a whole lot that we can do to keep that consistent.
Perfect. Thank you.
Yep.
Thank you. Eduardo Lobão from Aerospace Technology Institute, UK. Do you guys plan to include noise measurements in the database? And also, second question, despite those unintended deviations, is there a plan to include intended deviations to actually get some typical variations that might happen?
Yeah, I didn't quite catch your first question, but I'll answer the second one first. Yes, there are recommended good practices for the deviations in the measurements. Those are within the paper. So, and can you repeat the first question?
Oh, the first question, if you intend to include noise measurements, aeroacoustics.
Oh, aeroacoustics. So we haven't, to date, we have not seen a huge amount of aeroacoustic testing. There's been a little bit of data generated at ONERA specific around that. We've kind of, within the official definitions of the ecosystem, we've kind of shied away from that subject a little bit and are leaving it to the individual partners to define what that looks like. So I think ONERA has a data set specific to noise. JAXA is building a model that is intended to explicitly look at aeroacoustics. I think we'll look at it with the Boeing model at some point. So there's a bunch of work being done there, but there's not so much to document, I guess.
And it's conceivable that some of that data, some of that aeroacoustic data could be part of the ecosystem data sets that are available. So that's something to think about in the future as we start getting that kind of data. Any other comments, questions?
You exercise a little. Chris Rumsey, NASA Langley. You mentioned that toward the end there that you have, it's more important that you get the flap overhang and slat overhang and gap, that's more information. Is that something partners have already measured, or is that
No,
something
that's
going
new.
forward from
That's
from
new.
now?
Yeah. So
Oh,
we put it in this paper, and I plan to, I guess, individually get with the partners and say, hey, can we actually
Can we
capture
get
this? There's been some instances, for example, on the NTF model, where we were there, we actually explicitly measured the gap, which is one of the most critical features. So bits and pieces. The other kind of gotcha there is if you don't plan on, for example, measuring deflection, it gets very hard. So if you don't build in, reference planes for what is your deflection relative to, it gets very hard to do after the fact.
Right.
So some of that is too little, too late. But we're kind of doing what we can to, get that data.
Great.
All right, thanks. Let's move on. Let's next speaker. So our next speaker is Melissa Rivers. She manages a reduced life cycle cost sub-project under the Transformational Tools and Technologies project at NASA. During her 36-year career, she has supported numerous research studies, but her primary duty over the last part of her career has been development, testing, and analysis phases, including the CRM and the high-level CRM.
Thank you. Good morning. I'm going to be talking about the NASA contributions to the high-lift Common Research Model ecosystem this morning. Okay, first a brief outline. I'll talk about the background. I won't go too much into that because you've already heard a lot of that. I'll talk about our model design and fabrication of the two models that we have, and then I'll present some of the data from the recent tests that we completed. We've done 3 different tests on this model, and I'll present some data from all 3 of those tests. And then we'll look at some of the comparison to the partner data that you've already seen some of that. Okay, just a little bit of background. I think Adam and Jeff mentioned the 10% scale high-lift common research model. That model was built after the initial reference configuration was developed. It was tested in the 14 by 22 foot subsonic wind tunnel at NASA Langley in the winter of 2018. The focus of that test was active flow control, but toward the end of the test, we were able to get some conventional high lift data, like 3 days worth or so, but it was some test points that we could use. A year later, we took the model to the Kinetic 5-meter tunnel in the UK. There, as was already mentioned, we refined the device positioning and the, I guess I'd call it official reference configuration was defined. From there, NASA agreed that we would build 2 additional CRM high-lift models. The focus of these would be to be tested in the National Transonic Facility, the cryogenic facility at NASA Langley. And we would test up to flight Reynolds numbers. So this would be something unique on these 2 models. The first model was to be a 5.2% scale semi-span model. It's modular, as was mentioned, in landing, takeoff, and cruise configurations, and I'll show the different pieces in a few slides. The second model was a 2.7% full span and semi-span model, and I'll explain more about that later. It's also modular, but we only built landing and takeoff configurations. We didn't build the cruise configuration for that one. Okay, first in design, we started with the 5.2% scale model. And here we have pre-existing fuselage. We had to build new fuselage fairings. We had an existing nose and tail assemblies, but then we had to build the leading edge, the slat, nacelle assembly, landing gear, main spar. All of the rest of it we designed and built. The landing configuration, we built 3 different inboard flap angles. The nominal, which is 40 degrees, and then +3 and -3 degrees. The outboard flap angle, the nominal 37, and then plus and -3 degrees on either side of that also. The slat angle was 30 degrees inboard and outboard as defined in the reference configuration. And then for the takeoff configuration, we left the inboard and outboard flap angles at 25 and the slat angles at 22. All of these were defined for the reference configuration. Okay. And then for the 2.7% scale full span model assembly, we already had the nose, the upper fuselage, the 2 aft fuselage parts, and the horizontal tails. We had to build the nacelle pylons, the landing gear, the lower fuselage, and the wing assemblies, but included both the slats and the flaps. Let's see. For the semi-span model, what we are doing is taking the left-hand side of this wing, and we have built, or are having built, a new fuselage that will be just a semi-span, just a semi-span fuselage that will mount to the wall of the NTF, just like the 5.2%. So, with this, we'll be able to have a look at the difference between the 2.7% and the 5.2% semi-span, see what the scale difference does. But also, we will test this same wing, both full span and semi-span. So, let's see. Okay, and then for the model pressures, as was already mentioned, there were 10 rows of pressures defined. We did on the 5.2%, we included all 10 stations. On that model, we had 309 pressure ports. The number varies a little bit depending on if you have deployed flaps, deployed slats, or if you're in the cruise configuration. So that's, these numbers are for the reference landing configuration. And then we also had 12 coulites connected during the recent NTF test. We do have 16 installed that we can use, but we were only able to connect 12 this past time. The 2.7% model pressures, they're a subset of the 5.2%. Since this model is a lot smaller than the 5.2%, we don't have quite as much room in each wing for the pressure routing. So even though it looks like we have more pressures, it's split between the 2 wings. So we have 315, but it's split. We did have to take out one of the rows to be able to fit the pressures that we felt were most important in the wings. So we removed station 6 from the 2.7% model. On the semi-span wing, on the port wing, there's 189 pressure ports. There are 8 nacelle pressures built in, and there are 8 coulites installed in this model. Okay, something else different about this model is we were able to 3D print both the nacelle and the landing gear. For the nacelle, what we were really excited about was we were able to build the pressure taps into the nacelle itself. So there was no routing, there was nothing, needed whenever it was fabricated. And for the 2.7%, we were able to have 8 pressure taps built into that nacelle. For the landing gear door, let's see, that you see right here, and the landing gear itself were fabricated separately and then attached. Okay, and then I'll get into the testing of the 5.2%. The first test of this model was done in the 14 by 22 foot subsonic facility, as I mentioned. It was tested in the fall of 2022. We went ahead and did this as a checkout test. We wanted to check all of the different parts that we had built, just to make sure everything fit, make sure the parts were what we were expecting. So we were able to test all of the configurations, all of the different model parts. We tested at the landing and the takeoff Mach numbers of 0.2 and 0.26. We ran at angles of attack from -4 up to 24 degrees. And because of this test, we did find several, I don't want to call them issues, but several things with the model that we could go ahead and update or fix. There were some model changes that were really, really difficult. They looked good on paper, but whenever the technicians actually tried to do the model change, it was a lot more difficult. So we were able to go ahead and make those changes. And that was before we sent the model over to the low-speed wind tunnel at Braunschweig. We tested this model at DLR in Braunschweig in the spring of 2023. I will mention that the fuselage, was not the same as the NTF model, and the balance, it was a different balance that was used. Another thing that I'll go ahead and point out is on these semi-span models, we have to use what we call a standoff. And this standoff height for the 14 by 22 test, the DLR test, and for the NTF test were all different heights. Okay, so at this test, DLR was able to test all three configurations, the takeoff, landing, and cruise. DLR also tested a Kruger and a nacelle that they designed, and lots of data was collected. Ralf will give more information about that next. But forces and moments, model pressures, PIV was done, mini tubs, oil flow, and aeroacoustic data was obtained during that test. Okay, and then finally, we were ready to test in the NTF. The schedule finally was able to accommodate us. So this model, as I said at the beginning, was designed for the NTF, so it can withstand temperatures from -250 Fahrenheit to 120 Fahrenheit, a maximum dynamic pressure of 380 PSF, angle of attack -4 up to 22 degrees. During this test, we had planned to test all three configurations, but we were only able to do landing and takeoff. We ran out of time and weren't able to do the cruise during this test. We were able to do air and cryogenic runs, so we were able to get Reynolds number effects, which I'll show some plots in a little bit. During this test, we collected force and moment, model pressures, wing deformation data. We also looked at the nacelle on and off, the landing gear on and off, and we looked at the tail effects on this model. Another thing that I didn't mention, but we did do some I-shape testing during this test. And I'll just leave it there. Okay. I just wanted to put a picture of the run log up just so you can see how many different Reynolds numbers, how many different Mach numbers, all of the different configurations that we were able to get during this NTF test. Okay, and then just to show some of the data, first look at the short and the long-term repeats. So this is a Reynolds number of 3.33 million. I show both short-term and long-term on this plot. The short-term was the same day, so we did one run, at a certain Mach and Reynolds number, and then we would do some other runs, and then we came back and did that run again. And then the long-term was almost 2 months later. We ran the same exact condition. And as you can see, the repeatability looks good at 3 million. And then the same thing at 5.49 million. The short term was again the same day. This time, for long term, we didn't have to wait quite as long. It was only 2 weeks instead of 2 months. And again, the repeatability looks good. Okay, now I'll just show some of the effects that we were able to test. First was the nacelle effects at 3.3 million. Here you see the nacelle off is the blue circles, the nacelle on are the green circles, and this looks as we would expect. And then at 5.49 million, the same. Okay. And then the tail effects at Reynolds number of 3 million. Again, tail off is blue, tail on is the green circles. Okay, and then for a Reynolds number of 5.49 million, the same thing. Okay, and then just looking at the landing gear, on and off. Again, off is blue, on is green, and everything looks like we would expect for these 3.3 and 5.49 million. Okay, and then we were able to look at the Reynolds number effects. We tested from 1.6 million up to 30 million. And as you can see, as we go up in Reynolds numbers, the lift does increase. There's something going on with the pitching moment over here as we increase in Reynolds number, but we haven't dug into that yet. Okay, and then just a quick comparison to some of the partner data. First, I looked at the same configuration, landing, nacelle on, tail off, at the landing condition of 0.2 and a Reynolds number of 1.6 million. This same model was tested in NTF 14x22 and NWB, as I mentioned. So the fuselage was different in DLR. The standoff heights were different in all 3 tunnels. But as you can see, they do compare pretty well across all 3 of those tunnels. They are at a little bit of a different, 14x22 was at 1.52 million instead of 1.6, but okay. And then, as you've already seen, we add the KHI data, which was another partner who had a test before the NTF test. And as you've heard about the AERODYNAMICS data, you see the KHI, which is the purple upside down triangles right here, mixed in with the blue right here. It compares really well to the NTF data, while, as you saw before, the AERODYNAMICS data, it's a lot higher lift than what we were predicting in NTF. So we looked into that a little bit closer, just to see what the actual difference looked like. And it is about a 0.2 difference in lift between NTF and AERODYNAMICS. Okay, this is at a 5.9 million Reynolds number, and again, you still see about almost a 0.2 difference in the lift between the two tests. As was mentioned earlier, we have looked at everything we can think of, geometry differences, the way things were tested, you know, all different things that we've been able to come up with and that other partners have suggested that we try, and still we have not figured out the root cause of this delta, but we are still looking into it. Part of the investigation is the I call it the surprise 14 by 22 test that will be happening in the next couple of weeks. With that test, we hope to be able to get some flow visualization that will show us where the differences are between this model and the Honora model. Okay, and then just to kind of summarize or to finish up, these models will be tested some more at NTF. Next up is the NASA 2.7% scale full span model. That test is scheduled for December of this year through January of next year. In this test, we're going to just be focused on force and moment, model pressures, and wing deformation. The next test after that will be putting the 5.2% scale semi-span model back into the NTF. That test is scheduled for July of next year. And the focus on this test will be mainly the flow visualization of the surface and the off-body. We have several new techniques that have been developed specifically for this model that we'll be trying out next summer. Okay, and then the final test, as of right now, will be the 2.7% scale semi-span test, where we're going to take that same port wing and test it on the wall, as you see here. That entry is scheduled for late 2025, and there we will focus on force and moment, model pressures, and we'll take wing deformation and compare what we get from that semi-span test to the 5.2% semi-span test. Okay, all right. Any questions?
Okay, we have time for questions?
Well, I think I've got a bit more information about my previous question. So, well, coming back to the Honora and comparison between Honora and NTF test. So it's like, it's not only the CL max, which is different, but it's also at low angle of incidence you have some sort of difference. But what is quite interesting is that you've mentioned that, okay, we've checked the geometry and all that. But personally, I think it's the flow which is different, because if you look at the slope of your lift at very low incidence, I would expect it to be sort of linear, assuming that you haven't reached a condition where you can start having separation, or what we call low-speed buffet. And you can already see that there's a bit of a change in slope. So I think that the devil is in the detail, which is the flow measurement, the characterization of the flow. Well, that's my personal, it's not really a question, it's more of a comment.
Yeah.
Any other comments or questions? Yeah, so trying to characterize the flow in the tunnel is a challenge, okay? There's no doubt about that. And so we do our best to try to understand, for example, with the semi-span testing, what the floor boundary layer, for example, is, and whether or not we are predicting that, for example, when we do internal safety.
Well, if there's no other questions, I mean, because when you quote the Reynolds number, basing it? Are you basing it on a average chord or the root chord or mean aerodynamic chord, right? But then you have quite a bit of taper as well. So going outboard, your Reynolds number is changing as well. So in fact, you might not be getting the same kind of flow topology, which becomes very problematic once you have very high angle of incidence. You might be generating a leading edge vortex where the lift contribution is actually completely different. You have sweep and taper.
Right, but nominally we're running the exact same configuration, right? So.
And that's the difficulty is, we believe we are running the same configuration, the same geometry, but where are the differences coming from? And we've checked that. We've checked between the models to make sure that we have the same geometry. As was shown in Adam's slide, we know there are differences, but we don't expect any of those to make this big a difference in lift. Yeah, it doesn't make any sense, but it is where it is right now.
Okay, well, I'll leave it at that. Let's thank our speaker. Okay, our last speaker in this session is Ralf Rudnik. He's the head of the Transport Aircraft Branch at the Institute of Aerodynamics and Flow Technology at DLR in Braunschweig. He has a PhD from the Technical University of Berlin, and his areas of expertise are high lift aerodynamics, engine airframe integration, and CFD, and turbulence model validation.
Thanks, Jeff. Hello, everybody. I'd like to present our contribution, the DLR contribution to the CRM high lift ecosystem, and Melissa already gave you a small teaser. I'd like to introduce the co-authors of the paper, that is Sven Pulm, Florian Schmidt, and Jochen Wild. They took care for the component design, and Sven was ahead in charge of the test campaign. And we have Mr. Schröder, Mr. Speer, Mr. Mühlmann, who are measurement technique experts. So let me give you a brief overview of the talk. I will talk a little bit about the motivation that we had. We took a slightly different route compared to other partners. Then talk about the configurations that we tested and the test facility and the experimental schedule very briefly. I'd like to give you a flavor of the results that we collected. I'm going to not go through all the details, but just take the different measurements that we took to outline features and aspects that we looked at. And that is, as Melissa mentioned, forces moments, pressure distributions, PIV, flow viz, transition detection, and acoustic measurements. And then I will conclude and give you a brief outlook. Let me start with our motivation for this test. Well, Jeff put it very good, the first presentation. The CRM ecosystem is of great relevance for DLR as well, due to its comprehensive experimental database, and that helps to detect, investigate, and study inconsistencies and uncertainties. We've seen some of them. But also making use of the comprehensive numerical database for developments that we do to our codes. There the CRM is a really good candidate to check algorithms, improvement in turbulence models and stuff like that. But we do see a need for an extension of the experimental database, addressing specific requirements that we had. And I listed three. The first one was to investigate in detail wall and mounting effects, because the purpose that we use these validation data is CFD evaluation, especially scale resolving computations, which turned out to be much more reliable than the RANs as a result of the high lift prediction workshops. We intended to generate a feature-rich validation data set in a well-known facility, and also to assess the impact of configuration variations, which I will outline briefly. The basis is 5.2 NASA CRM high lift, as Melissa pointed out, and the framework was a DLR internal project called ADAMANT, which stands for Adaptive Data-Driven Physical Modeling Towards Borders of the Envelope Application, and of course a NASA and DLR collaboration, which has been the basis for this test. Okay, let me come to the configurations and the wind tunnel model variants. The baseline configuration, as mentioned, has been the 5.2% semi-span model used for cryogenic testing, ready for that. The configuration variation that we introduced is defined by an exchange of the leading edge slat by a foldable bullnose Kruger, VFBK, and at the same time an exchange of the reference nacelle against a UHBR, so a larger nacelle with core body. And you see both model variants here on the right. This is a reference or baseline NASA CRM, and this is a DLR variant. The design has been done based on RANS tools that we used here. It has been constrained. The design target was to achieve, let's say, comparable high lift performance for both models in full scale. And that means also without tracks or links, just taking the high lift devices as they are on the model. And well, the constraints are that, of course, we were not allowed to change the model, which is understandable. So all pieces had to fit into the original model and its component. And for instance, the trailing edge flap wasn't touched. So you might want to adapt the trailing edge flap if you design a Kruger. That wasn't possible, but that shouldn't be a big problem because the intention of the design was not performance optimization, but create validation data. And the second consideration was to allow an arbitrary change of the components, which we did. That means we exchanged the slat and kept the NASA nacelle and also took the UHBR nacelle and tested it with the NASA slat. The DLR components are nacelle pylon, the Kruger, the fixed wing leading edge had to exchange and fabricate it as well. And they have been fabricated out of carbon fiber material, but also out of cryosteel. Melissa mentioned that the fuselage also changed, as you can see here from the black color. Turns out that it is about twice as heavy as the wing with a nacelle, so it was beyond the capabilities of our balance, and we fabricated a known fuselage for that, which is supposed to be geometrically identical to the original model. And there's a paper around there that outlines the design work that has been done on that. You see here a sketch of the Kruger that has been designed, and down here the nacelle with the core body. All right, let me come to the test facility and the experimental schedule that we had. As I said, the test facility has been the DNW NWB, the low-speed tunnel in Braunschweig. Test section setups that we looked at have been two. The closed test section, which you see in the upper picture. Test section dimensions are listed down there. But we also intended to look at the open test section. Usually you go for a closed test section for aerodynamic testing and the open section for acoustic testing. So the intention was here to do back-to-back testing with one model in order to identify differences, which I will come back later, and also to support the computations for that in order to assess and improve wind tunnel correction that have been applied. The test has been more or less divided into two entries. The first one in the closed test section was the one where the focus is on. That were 28 days in 2023, where the 3 Mach number tested and the Reynolds number range was moderate from 1.2 to 1.8 million. And as we have atmospheric conditions, we do combinations of Mach number and Reynolds number for that. We tested the landing and the takeoff configuration and the DLR and the NASA variant of the CRM high lift. For the open test section, 8 days have been scheduled. Mach numbers range between 0.15 and 0.2. And again, landing and takeoff configuration has been tested. Takeoff is a little bit more attractive for noise reasons, for acoustic testing. And both variants have been tested back to back. You see the open test section down here, We have a semi-span model which needs to be mounted, so we took a floor, and this setup is designated as 3/4 open, if you will. And you see also the anechoic chamber, so the tunnel has fairly well acoustic properties, I would say. And on the sketch, you see the closed test section, and this is the anechoic chamber and the open test section down there. All right, let me come to the results. I start with forces and moments. And the first has already been shown by Melissa. That is a comparison between the D&W polar, NASA configuration, landing, reference conditions. Melissa mentioned that Reynolds number has been close but not really matching. And you can see that the data know each other, which is a good notice, I would say, and are fairly close together. Even the pitching moment is in close proximity. So that was a reason to go on with these tests and be sure that the basic model setup in the tunnel should be okay. The graphs are a little bit busy. I tried to talk you through that. This is a comparison of the NASA and the DLR variant in landing configuration, and at the same time we have a variation of the Mach and Reynolds numbers. You see up here the lift curve, the 3 Mach-Reynolds number combination for the NASA model, and down here the combinations for the DLR model. So if you go to reference conditions, that is Mach number 0.2, we have a degradation of CLmax of about 20 lift counts. Having the possibility to check and change the single components tells us that basically this is due to a separation trend at the outboard Krüger at these low Reynolds number conditions. As I mentioned, the design has been made for full scale, where we do or did match the NASA performance. So this is a clear low Reynolds number effect, and it's also attributed to the links or the brackets of the Krüger, which have been designed, let's say, following the slat tracks or the slat brackets, as we didn't have the freedom to adapt them. So half of that is due to the brackets, and half of that is due to the low Reynolds number. The trends here in terms of this Mach Reynolds number variation, which again is very mild, is consistent. So the higher the Mach and Reynolds number, the higher CLmax is. The differences are somewhat larger for the DLR configuration than they are for the NASA configuration, which tells us that this outboard separation is low Reynolds number induced and tends to react more on the Reynolds number variation than for the slat. Pitching moment are very comparable. Differences are small. In general, we have a little bit less nose-down pitching moment for the DLR configuration, which is good in principle for trim efforts, but not decisive in this framework. Okay, next result for forces and moments is a comparison of the closed and the open test section for the NASA configuration. You see in red lines the lift curve for the closed test section, and in black the open test sections. All data have been corrected for wall and mounting effects and jet effects. And the discrepancy is about, or the difference, about 5 lift counts, which tells us that there is an effect, even if you correct. We correct it classically following the Argado graph 109. In the linear range, data are pretty good, comparable. And as you usually test, as I mentioned, the open test section, not for CLmax, but for acoustic reason, where the linear range is of concern. This confirms that the setup is suitable. On the other hand, it will be a nice test case in order to get a better grasp on these effects comparing the 2 test sections. Pitching moments are pretty close to each other, so there's not a big difference in them. And that brings me to the pressure distributions. Again, just a flavor. One example, we see 2 pressure sections of the DLR configuration here. The first one is section B. It's the inboard section, 3 elements. And the second one on the right is the outboard section H, which only has 2 elements, as the flap has already ended there. Looking at the angles of attack, we go up from 8 degrees to 15 to 19 beyond CLmax. And if you look at that, you see that basically the inboard section is okay for that. And that the lift degradation or the lift breakdown is triggered by the outboard section here on the slats. The blue curve is the highest angle of attack compared to the other one, and you see the drop. And you also see the separation on the fixed wing. All right, that was the example for the pressure sections. PIV has been mentioned, particle image velocimetry. We did tests for that as well. We decided to go for longitudinal sections in that case due to observation reasons. And in order to capture as many data as possible, we had a strong refinement at the nacelle in order to capture nacelle wing interference effects. With the PIV, you see the laser sheets in the middle, and we have all in all 15 sections, 14 distributed behind the nacelle, and one outboard section in order to observe the outboard region, which is prone to separation too. Just as an example, we see two pictures on the right. The first one is a time-averaged velocity field, U component, high velocities in red, low velocities in green and blue. What you see if you look at that is specifically here the low speed area, this green dot, which corresponds to the nacelle strake wake cutting these, the slice. Down on the bottom, we have instantaneous velocity information, which gives you an idea of the turbulent structures that we find here. And the idea is, with this time-resolved PIV, to provide data that are suitable to derive Reynolds stresses, so we can compare the scale-resolving computations that we do to the PIV measurements in terms of Reynolds stress. All right. Let me come to FlowViz. We all know that the NASA configuration has a distinct trend to separation in slat track wakes. And we did oil flow pictures of the outer wing area. You see on the left the two pictures here, Mach number 0.2, 13 degrees angle of attack, and 19 degrees close to CLmax. The separation areas are indicated by dashed red lines. If you look at that, you can clearly see the widening of these separated areas. And we did at the same time some tuft visualization. And the shape of the single tufts here is an indication for their state. So we have attached flow. The triangles correspond to excited tufts, and the shapes down here correspond to flow separation. If you compare the two, well, the tufts give an indication where separation starts, but of course they are not, by far not as valuable as the oil flow pictures are. Maybe a reason of resolution, so you want to bring more tufts on the wing, but at some point, if you have a high tuft attachment here, then you start to have an impact on the flow, so that's maybe not the way to go. Next point is the transition detection. We took infrared pictures for all configurations in the closed section, and this is an example for the NASA variant in landing configuration. We had 3 cameras, 2 looking at the midboard wing, that is cam 2 and cam 3. You might recognize the nacelle down here. And 1 cam looking at the outboard section. We are in a Reynolds range of 0.5, 0.6 million, so usually it's not too critical for laminar effects, but you want to check that. And that's what we did. And it was at the same time a check for the wing transition dotting. We had dots at the wing roots, behind the nacelle, here at the fixed wing leading edge, at the slat cutout, and at the outer wing, and on the nacelle and the fuselage nose. So these have been taken away, and they have put on, measurements have been taken. And at the same time, we also did a checkout between track 13 and 14. apply the trip dot row there and see the impact. All in all, the effect of the trip dots was negligible. There was no real impact on the measurements, trip dots on and off. We didn't detect any enlarged areas of laminar flow. For positive angles of attack below -2 degrees, there were some, but this is not the relevant range of where we look at. And at the same time, you might see at the high angles of attack here some dark areas on the slat, which corresponds to laminar separation bubbles. And that is a challenge for transition prediction, which we want to apply to this configuration. And of course, it's always helpful to see how large is the impact. Usually you have to have a really high resolution if you want to resolve a transitional bubble, but the effect is another thing. So we will look into this as well. And again, it's a very nice challenge to our methods. And okay, there's a paper around there outlining a little bit more in detail these measurements. Finally, I'd like to briefly touch on the acoustic measurements that we did. I mentioned that we have an open test section, kind of, and a closed test section. So that was an interesting setup to check the capabilities. What we did was applied microphone arrays in both sections. Down here you see the wall array in the closed test section. Up here is the wall array in the open test section. In the open test section we also had single microphones in order to combine these measurements and not only get source information but also pressure sound level information by doing the appropriate evaluations. This is all ongoing work. There has been a paper out for the acoustic measurements in the closed test section, and here's an example. It's a frequency plot, a source localization, and you clearly see the large impact of the slat tracks here for this configuration, which is really expected. All right, this brings me to the conclusion and outlook. We did some low Reynolds number tests with a 5.2% semi-span model in the low-speed wind tunnel Braunschweig. We introduced a configuration variant by a modified leading edge and a different nacelle, and did combinations of both. The UHBR nacelle is representative of a bypass ratio of about 15. We looked at takeoff and landing device settings together with some variations of the span-wise flap gaps. This has been mentioned by Clark. So we checked a sealed or partly sealed and an open gap, and also did variations of the chine as a side study. We did back-to-back testing of the main configuration variants and settings in the closed and the three-quarter open test sections, and performed classic measurements of forces, moments, pressures on the wing, but also did some flow field measurements using PIV, flow surface visualization, and aeroacoustic measurements on both variants. It's a huge data set, so it's still under evaluation. We publish things continuously and also intend to bring the data to the CRM ecosystem. I think the first data set maybe is on its way, the CRM NASA configuration. So at the end of the day, most of these data are supposed to be publicly available once they have been evaluated and published. The internal validation using the scale resolved computations is about to start. Computations are quite cost and time intensive, so we are about to continue what we have done in High-Lift Prediction Workshop 5 and compare the experimental data, internal simulations, and pre-flight against the data that we have collected here. That's all I have for the moment. Thanks for your attention. I'm happy to take questions.
Any questions for Ralf?
Thank you for a very interesting presentation. Have you painted the wing black?
Sorry?
You've painted the NASA wing with a black paint or something for a PAV?
No, that was a carbon fiber piece. So that comes in black.
So were there any issues with PIV on that model?
Well, you have Yes, you have to make sure that there aren't any reflections, of course. Either you take the natural paint or you apply foils in order to make sure that this doesn't happen, of course, yeah.
So
We had,
the
sorry?
surface. You modified the surface, yeah. You modified the surface of the.
We
of the
applied
wing.
foils,
Foils.
or if the
Okay.
color is already black, you don't have to do much on that because you don't have reflections.
Okay. So the surface roughness of this foils are basically similar to the original surface.
Well, they come in, now I have to really think about it, they come in two different roughness sets. We tested both also for transition, and it turns out that they don't have a big impact, so I think we took the rougher one, but I'm not 100% sure. So you can take it off the shelf, basically, it doesn't have a big impact.
Thank you.
Any other comments, questions? All right, let's thank our speaker. So the session is concluded. We'll meet again